Hello everyone. So let's learn dynamic programming by examples. Um, Now, the first one is, the traditional Fibonacci problem, where to reiterate, the Fibonacci sequence is the sequence where, and at any, any number is the summation of the previous two numbers that are encountered in that sequence. So more concretely, what I want is basically, if I ask you to give me the seventh number of this Fibonacci sequence, you are supposed to tell me that it's 13. If I ask you what is the ninth number, you're supposed to tell me, it's 34. Now, so what we promise is basically, for each problem, we are going to see basically three solutions. So the first solution will be the naive recursive way, where we will start from the top and break down that problem in top-down manner. Okay, so this is the first solution that we are going to follow for this problem. So once again, if I give you any number, if I ask you what is the sixth number or what is the nth number of this Fibonacci sequence, you are supposed to tell me, what is the, let's say, how will you calculate that seventh number or that sixth number of this sequence, which is, let's say 8. And the property of for the answer is that, the answer, the nth number will be the summation of n minus 1th and n minus 2th number. Okay, now we can follow top-down strategy, and by top-down I mean that we can start, let's say if I ask you what is the seventh number, we can start from that. Okay, and then we can say that, okay, the seventh number will be the, the sum of the sixth number and, the fifth number, whatever those numbers are. Okay, and then solve this problem iteratively, solve the sixth number, which will be the, the summation of the fifth and the fourth number, and so on and so forth. Okay, so this is the naive way of doing this recursion. Okay, take the number nth and call this function recursively for n minus 1 and n minus 2 number. And because I'm so short that, for nth number, the answer is the summation of, the previous two numbers. Until and unless we reach, our base cases, and the base cases in this, in this approach is whenever you reach, the first two numbers. So what we are given is that the first number is 1 and the second number is also 1. And so once we are given that, we can assume that the first two numbers represent my base cases, in which case I'm supposed to return 1. Okay, so whenever you encounter, let's say, the first or second number, you are supposed to return 1. Okay, so the first and second numbers, you basically represent your base cases or your leaf nodes. So this is the overall, recursive way of, implementing your Fibonacci, sequence. And by that I mean, returning any number at a particular slot of that sequence. Now, in the remaining video, what we are going to discuss is, this time and space complexity of our recursive top-down approach. Okay. Right. And so first we need to discuss how have we, like basically, we have already told you the answer that, the time complexity is upper bounded by, 2 to the raised power n, and, lower bounded by 2 to the raised power n, n by 2. But how do we come to this conclusion? So imagine that, here we have basically two recursive calls, one for n minus 1 and one for n minus 2. But imagine that, we make our life easier by saying that, let's say that the function calls itself recursively by reducing, this number n by 1. Now, in that case, what we can have is basically, imagine that, n is equal to 5. We start by, recursively calling foo of 4, but you see, we don't go to the right child. We only stay to the left child. Okay, and then foo of 4 calls foo of 3, foo of 2, and then foo of 1. Okay, and then obviously, when we come from foo of 1 back to foo of 2, we also need to evaluate, there's this call second time, which basically moves you to the right child of that particular parent. Okay. So in that way, for every, nth number, we are calling, foo of 4, foo of n minus 1 a couple of times. Okay. So that, that is why for every parent we have 2 children. Now okay, so what is the time complexity of doing, this approach? Well, obviously the time complexity is, the total number of nodes within this tree. Okay. And what is that? So we know that, the total number of, the at nth level, at nth depth, we have 2 to the raised power, n children. So if, let's say, if n is 5 in this case, I know that, the depth of this tree is 4, for example. So the top root node is at 0th level, and so therefore we will have n minus 1 levels in that tree. And at any level, the number of children will be 2 to the raised power whatever that level is. So here we have, just one child in this level. At n is equal to 1, we have, 2 to the raised power 1 child and children. And likewise, at this level, we have 2 to the raised power, 3, 2 to the raised power 2 child, which in this case is 4. So if you want to sum up the nodes, you'll start from the bottom node and, move up. And this is also something that I already mentioned, that if you take children at any particular level, let's say, for example, if I talk about, the second level, 1 plus 2 is, 1 plus 2 is 3, and obviously 3 is, 1 minus 4, basically. So the number of children at this level is whatever the summation of children at the previous 2 levels plus 1. Okay. So likewise, 4 plus 2 plus 1 is 7, and 7 is, less than 8, or let's say, 8 is equal to 7 plus 1. So at any level, the total number of children within that level will be 2 to the raised power, n plus 1. Okay. So whatever your children is. So in fact, there is some typo. So 2 to the raised power n is basically 2 to the raised power n minus 1 plus 2 to the raised power n minus 2 plus 2 to the raised power 0 plus 1. Okay, so this plus 1 should appear on the right side of this equation rather than on the left side. Okay, so at any level, the total number of children that you have within the tree until that level is basically, whatever the children that you have at at the previous levels combined plus 1. Okay, so I know that since the total number of children, in that I encounter in this case is, somehow upper bounded by 2 to the raised power n. Okay, which in this case will be, 1 plus 2 plus 4 plus 8 plus 16. Okay, so which will be less than 2 to the raised power 5, or that will be equal to whatever the previous two, all the children until to the raised power 4 plus 1. So this is how we calculate, the total number of nodes, or let's say the time complexity within the tree. Now, so I remember, while discussing, trees in general, I have maintained my position that you can also say that, okay, the number of children within the tree is basically, upper bounded by 2 to the raised power n minus 1. But if you want to be more concrete and you want to, add, let's say all levels, then you can simply say that, okay, the total of children will be, all the levels combined, which in this case will be less than 1 less than 2 to the raised power n. Now, what about the space complexity? Now, if we look at this solution where we are calling, this function with, one decrement couple of times, what you can see is that, let's say if I start from foo of 5, I will call foo of 4 over here. And then, but you see, we don't go to the right child. We don't really get into this into this statement until and unless we evaluate foo of 4, and then foo of 4 calls foo of 3, then foo of 2, then foo of 1, and once we are at foo of 1, the function will return. So this call stack, this you know so whenever this recursive implementation is implemented at by compiler, the compiler maintains a call stack of of all these functions in memory. So we need to have, so at this point, when whenever we are let's say at n is equal to 1, the function will return, and when the function will return, the call stack will be destroyed. So the space allocated to that function in memory will be deallocated. Okay, so once we return from this base case and move into this 2, and then this 2 will call this one. And so at any time within this call, you'll see that at most we will have 5 functions allocated on top of each other in memory. Okay, and so therefore the space required will be order of 5 or order of n in that case. So whatever the n is, at most you will need to maintain 5 functions or n functions within your memory. And so therefore the space, and since at the each function only contains a constant amount of memory, so therefore I'm sure that that the space complexity of this function is order of n. Now what about if I simply said that instead of n minus 1, now you will have to do this n minus 2. So you will have to call this function recursively, but with the argument or let's say a decrement of 2. Now in this case, everything else, the argumentation remains the same, but what we can simply say that now the function, the height of the tree will be reduced by half. Okay, so if we call start from 8, foo of 8 will call foo of 6 couple of times. That is why we maintain 2 children per node, and likewise foo of 6 will call foo of 4 once again couple of times, and so on and so forth. So the only difference between here and in here is that the height of the tree will be half in some sense, and so therefore the space and time complexity will also be halved. Okay, so whatever the space and time complexity in that case, n will be replaced by n by 2. And so this means that if I call this by if this function call is decremented by 2, the complexity is basically reduced by half. I mean, not half, but the the n is actually replaced by half, and so the time complexity or space complexity it depends upon, since it depends upon n, n is halved in our case. So this means that if I call this with n minus 1 as well as n minus 2, any recursive call, I'm sure that if this was for example n minus 1, I will have complexity of order of 2 to the raised power n, and space complexity of order of n. And likewise, if this was n minus 2 plus fib of n minus 2, I know that I will have the space and time complexity described by this lower bound. And so therefore in this case where I'm calling this function recursively with decrement of 1 and 2, I know that the worst case time complexity will be order of 2 to the raised power n, and the best time complexity that I could have will be 2 to the raised power n by 2. So the time complexity is somewhere between that, and likewise the space complexity is also somewhere between n by 2 and n. And by that I mean that the worst case scenario is that you'll have to make these hops n times, 7 6 5 4 3 2 1, if you follow this left side of the tree. And likewise the best scenario is that if you follow the right side of the tree, where you are basically calling this function recursively by decrement of 2, you'll end up making these hops almost half of the times as you do to the left side of the tree. Okay, so this is how we concluded the time and space complexity being bounded by these numbers. Okay, so in the next video we are going to discuss a clever way of doing the same recursion.